Hey everybody, my name is James and I will be your webinar for today's, I'll be your host for today's webinar. Welcome to Building Resilient Energy Systems with Industrial Networking. With us today, we have two speakers from Moxa. Our first is Kuru Kuruvilla. He holds a master's degree in electric power engineering and has extensive experience in power generation, renewable energy integration, and distribution grids. Kuru has been awarded multiple U.S. patents for his work in power system operation and control. Throughout his career, he has held various roles in design engineering, application engineering, product management, marketing, and P&L management. Also joining us today is Hans Jen. Hans is a senior lead field applications engineer at Moxa and a certified IEC 62443 cybersecurity expert. He has over 12 years of experience in industrial automation and specializes in IEC 61850 digital substations, energy storage systems, and utility network architecture. Hans also is a frequent contributor to customer trainings and technical conferences. Let's go into some housekeeping items before we jump into our presentation. The webinar will be 60 minutes with Q&A at the end. If you would like to submit questions, we encourage you to do that. Just use that Q&A function in Zoom. We will also see the occasional poll question pop up. Please participate in those as well. We'd like to see your responses. The recording will be shared so you can go back and watch the webinar on demand. There will also be a survey at the end. We appreciate your feedback on the presentation. And with that in mind, I will pass it off to Kuru to kick off our webinar. Kuru.
Hey, thank you, James. Welcome everyone to the 2025 Energy Webinar from Moxa. So in today's session, we will start by discussing some of the energy industry trends and themes around those. Then we'll kind of move on to the solutions across various different segments that Moxa can provide. And specifically, we will dive deep into two of those segments, those being the battery energy storage systems as well as data centers. And then we'll kind of end the webinar by highlighting some of these specific attributes that you may want to look in a partner when you think about going into large-scale energy projects. So to start with, I wanted to kind of show a pictorial representation of an electric power grid. The grid, as you can imagine, is vast. It includes all sources of power generation, all sources of load, and all the infrastructure that is required to match the generation with the load. In order to kind of think about in more manageable chunks, at Moxa, we kind of look at about 5 different subsegments, because that helps us to localize solutions which are focused on those. So the first is the substation. So in a power grid, substation essentially is a point of delineation between power generation and transmission, whereby power is generated at a certain voltage and stepped up to a transmission voltage. And at the other end of the transmission line, the voltage is stepped down again to distribution levels. So you have substations both at the generation side as well as closer to the load. And on top of that, almost any large industrial load will have its own enterprise substations. So automating the substation is a key aspect of optimizing the grid. Then kind of continuing on, renewable energy is another source that is present either as a central power plant, such as like a utility scale solar plant as an example, or it could be distributed, whereby you have smaller renewable sources interspersed with load, and that has its own particular characteristics that needs to be managed appropriately. Going along with renewable is also energy storage, which has grown in popularity over the last few years. And energy storage essentially allows a better balancing of intermittent energy sources with load. Then moving on, you kind of go into kind of that enterprise substation or the enterprise power usage area. So this could include either critical power applications, including backup power, for key installations, such as hospitals, for example, or it could be other sources such as data centers, which are obviously growing in popularity now. And then lastly, EV charging is an important component, just because that kind of introduces some new paradigms, the way the loads are distributed on the distribution side. So in this webinar, we will kind of touch upon each of these 5 subsegments, and we'll dig a little bit more deeper into 2 of those, the energy storage and the critical power or data centers. So I wanted to start out with some industry trends. So the first thing to kind of notice is that if you look at electric power demand, and this chart is for the US, but I think similar growth is happening elsewhere as well. You can kind of see that the growth that is expected in the next 15 years for electric demand is significantly more than what it was for the last 15 years. And that provides a lot of opportunities and challenges, to make sure that we can seamlessly accept that amount of generation with, in many cases, the existing infrastructure in terms of the transmission and distribution system. Then we again expect all different sources of energy to grow, because the only way you can meet this type of explosive demand growth is that you need contribution from both renewable and non-renewable sources of energy. Energy storage, like we talked about, is now at a point where it can compete with alternative options for peaking response, such as a gas turbine peaker, and that again allows addition of those energy storage, and also creation of new different market structures where the grid operator can look at procuring a lot of these ancillary services, which are critical to keep the grid going. And then lastly, I think maybe a little sobering to say that a lot of the infrastructure out there is pretty old, and that again means that in many cases there's opportunity to upgrade, for example, an existing substation or an existing distribution control system. So just building upon those kind of drivers that are happening, highlighting some of the themes, right? So the first of which is improving grid reliability, and in simple terms, that means reducing the number of outages and reducing the duration of the outages if and when one happens. Obviously, there are multiple drivers, for an electric grid operator, to focus on that. The first of which is there's loss of revenue. Anytime you lose power, there's a loss of revenue for the entity. But there is also other costs. There is cost of troubleshooting, so you need to have a truck roll, and on top of that, depending on the jurisdiction, there may be regulatory penalties. So improving the grid reliability helps the bottom line of the electric utility. Secondly, integrating renewables, especially distributed renewables, since they are very closely located, with other loads. Other criteria such as making sure that these sources don't island with the load that is already present. In other words, if the distribution system loses its connection to the main transmission system, there should be mechanisms to ensure that the islanding of these distributed sources do not adversely impact the power quality, the voltages, etc. So that requires some sort of active control, whereby that condition is realized and appropriate measures are taken, such as potentially shutting down a small solar plant, as an example. Energy storage, we kind of talked about, but there are multiple market applications, including in many cases, because of the limitation in the transmission infrastructure, some of the renewable energy that is generated cannot be used or cannot be used by the grid, at which point in time, without energy storage, today you'll be spilling that energy. Energy storage allows you to store that energy and then sell it back to the market at times when the transmission conditions improve. And on top of that, there are market opportunities, such as energy arbitrage, where depending on the time of the day, you can decide to sell power back to the utility at times of high pricing. And in addition, there are other mechanisms for ancillary services, such as frequency control and so on, which the energy storage provider can participate in. Now, kind of getting on the load side of things, there is a lot of load growth like we saw in the previous chart. And I think one of the things to keep in mind is that, a lot of the load is being added to existing, locations on the distribution grid, which may not be optimized for taking the amount of energy that is required. So this also gives opportunities to add, more advanced distribution automation, type controls. Getting EV ready, this is kind of a subset of that load growth problem. It's just that, the visibility that the utility has to where those, charging infrastructure is located and what is, kind of the real-time situation in each of those, improving the visibility and potentially even including controlling, some of the sources by the utility also becomes important as these these charging stations grow. And last but not least, security threats are obviously very important, so both cybersecurity side as well as on the physical parameter. I just wanted to show like two examples, just to expand. So this is just a chart showing ancillary services that are procured by the grid. There are many forms of it. Let's just pick frequency regulation as an example. Frequency regulation essentially means that the grid is always trying to keep the frequency at its rated. In the North American grid, 60 hertz, plus or minus 36 millihertz. In order for that to happen, one of the ways you can help balance it is using energy storage. Now, as an energy storage provider, you can elect to participate in that market, whereby you are guaranteeing that when you are called upon to either up or down regulate your power, you are ready and available to do it. But it also means that the grid operator is looking for some very stringent parameters in terms of, as an example, responsiveness. So if you get a power set point, then there's an expectation that you respond within a very limited time frame. And if you're not able to do it, or if your system is not designed to do it, then that means you won't be able to participate in this market. So this is an example where having a strong network and communication infrastructure will allow you to enable addition of yourself and participation into these marketplaces. Another example is on the distribution side. There's obviously a desire to reduce the amount of line losses. So these are losses that happen just based on the the physics of the distribution line. And there are multiple techniques to reduce these losses, one of which is called CVR, or conservation voltage reduction. This basically means that you are trying to regulate the voltage at different points in the grid optimally, such that the current flows are optimized and the energy losses are minimized. But for you to do that, you need to have good visibility on what the voltage readings are at those different points, because if you do not regulate it appropriately, you could get into an area where you are violating some of the distribution grid codes or ANSI requirements. So this means that you need to have the infrastructure to both sense, so the input-output functions, as well as taking that information and then communicating it back to the central control system so that it can make appropriate real-time decisions on regulating the voltage. changing capacitor bank settings, voltage regulators, and so on. So if you think about the grid from the last slides, there's a lot of talk we have on the physical domain. So this is basically all the equipment that is required for the power flow to happen. So everything from transformers to distribution lines to control equipment to that entire spectrum of transmission and distribution hardware. That area obviously has been in place for a very long time, and it's relatively mature in most cases. The area that is growing and that is important, for us to optimize the grid is the information flow layer, right? So the information domain where you have more and more sensors, you have more and more points that are visible to the control system, which includes having the networking and the computing infrastructure that is required to model, including using the latest AI and machine learning type techniques, right? So the information domain is where a lot of investment, right, a lot of growth is happening in order to squeeze the most out of the physical domain that is present today. So this is a survey that was asked where utilities were asked what are some of the major challenges that your teams face. And overwhelmingly, I think the response was improving reliability, right? So again, kind of going back to the previous charts on reducing the amount of outages and the duration of the outages. And then, closely following that in asset management, making sure that you have good visibility over the assets that are already present, includes everything from obviously identification, geolocating the assets, to the level of even having visibility over the firmware version, or having that real-time knowledge on what exactly is in the system, and then improving resilience, right? So resilience meaning if the system goes down, right, is there enough redundant parts, for the systems to go up and then come back to life as quickly as possible. So this is again from a survey. We are just curious. So there's a poll question, that will come up, just to get based on yours experience or the customers that you work with, right? What are some of the major challenges that you see? So I'll pause for a few seconds, just waiting for some of your responses. Okay, interesting. So cybersecurity for sure, right? And as we would expect, and even the previous survey, it was there. May have been slightly out of the top three, but definitely critical. Yeah. So I see some responses on EV charging, reliability, integrating DR. Yeah. So I think I think roughly you kind of see there is obviously concern areas across the board, and cybersecurity for sure. And I think maybe immediately following that, the integration of the distributed energy resources. So we'll talk about those two themes as well as we kind of get into rest of the presentation. So I'll close the poll and then. Okay, so now kind of moving on to some of the applications that we kind of talked about, expanding on that. So the first thing I think to notice is that although there are multiple segments we talked about within the grid, the needs are kind of very similar, right? So in almost all cases, there is some parameter you are looking to sense. So in the case of a substation, it may be a current or a voltage. In the case of maybe a renewable plant, it may be temperature or the solar irradiance. So it may be an ambient or environmental parameter. It may be an electrical parameter. Then typically those parameters need to be converted in most likely digitized, so that you can take that information and communicate that down the system. So this may include you're taking an analog value, converting to digital. It may be different protocols. It may be like an old serial device that needs to be connected to a modern Ethernet backbone. So there is an amount of conversion that happens. And once it's converted, then that information, that digitized information needs to be connected. So switching, routing, different cybersecurity principles, and having firewalls. And then ultimately that information kind of flows into a computing platform where some decision is made, either a centralized computing or in some cases it may be an edge computing, very close to where the source of the data is. And then once that decision, the analytics is done, a control system works, and that decision may be, for example, a set point that needs to be changed, and it basically follows that same path, back all the way to the ultimate device. So this is kind of a common theme, regardless of which particular subsegment we are kind of talking about. So if we kind of get into substation automation as an example, there are multiple parameters that are kind of looked at and optimized, but not all parameters have the same priority. So just to give an example, one of the things that is kind of monitored in a substation is the life of the equipment, right? So as an example, the life of a transformer. And that information, maybe a temperature reading, maybe an anomaly. So that information is collected, but that is not something that you take action on immediately, right? That's a cumulative impact. Over time, you look for changes in pattern, and then you make appropriate decisions. So this is an example of something that is not high priority, from a real-time perspective, and that means you can afford longer latencies. So it's not critical that the temperature reading goes back to the control center the next second. Minutes or hours of latency is perfectly fine. And then if you kind of go into the other end of the spectrum, you can kind of see there are things like maybe circuit switching or transfer trip that needs to happen almost immediately. So that would be high priority, which essentially means your system should have a very low latency. So it's very critical to have the architecture able to discriminate, right, and prioritize appropriately. Because if you prioritize everything at the same level, then nothing is prioritized. So one of the ways to kind of think about substation automation is, if you look at the left column, that is the kind of, we would say, the conventional or the traditional substation where pretty much everything is hardwired. So you, on the process level, you have devices. So as an example, let's say it's a circuit breaker. And at the bay level, you have protection relays, and the station level, you have some PLC system. Now, in this kind of the conventional system, everything is hardwired. There isn't much automation, at least on the process side. There is probably some serial communication at the higher levels, right, where you have serial devices, which are again kind of talking to the PLC. Majority of the substations, in the US, for example, still will kind of fall in that category. Now, if you kind of move to the center, you can kind of see, some amount of automation being started. So in this case, the process level or the connections between the end equipment and the relays, in this case, would still be hardwired, but then there is an automation happening at the station bus level, whereby the relays are communicating, to the power plant controller or the SCADA system in a digitized fashion. There are multiple protocols that are used. IEC 61850, as an example, is something that is very widely used, but then there are others, such as DNP3 and so on. And then on the extreme right is kind of the fully digitized substation, right, where even the communication going down to the end device is fully digitized. So you have RTUs, that are converting, for example, CT and PT voltage and current values, into a digital format. And then the entire substation is, fully digitized. So depending on where you are, in that transformation or the life cycle, there are different, ways we can approach the problem in terms of, okay, which areas do you want to digitize first and what solutions are appropriate. To kind of think about, just one example of, what this kind of means is that if you follow IEC 61850, you know that it prescribes, specific, timeframes in which your system needs to, recover. your system does include not just the primary power flow path, but also the communication system that is underpinning that. So if you take like the bus bar protection as an example, the expectation is that there is no downtime ever, right? Maybe what they call bumpless redundancy, which essentially means that you need to adopt techniques which are typically not very widely used in the automation world. So an example of what you would be able to use is called the redundancy protocols. And parallel redundancy protocol is one of the examples where in the schematic you can kind of see the orange and the green um, uh, local area networks. So you can kind of see the orange and the green, and here it's segregated. There are two different independent local area networks which are communicating the same packet, till you reach a certain point. And then on top of that, you can have a different redundancy protocol. This one is called HSR, whereby information is devices are connected in a ring topology, and information is transmitted on both ways, if you will, such that if any of the links fail, information still goes. This would be an example of bumpless redundancy because the two independent systems are constantly communicating, and even if one system is down, the other system takes over. So this is just an example. If you kind of think about the power world and redundancy, this is the type of expectations that are typically there. So this means that some of the equipment that is used needs to be also capable, right, of accepting, right? So just to give an example, this device called the red box or the redundancy box, this is something that you can connect to an existing relay, which does not have these redundancy capability, and you can immediately make it smarter, right? Whereby now this relay is now part of that redundancy network, whereby in this case, it could be a PRP or HSR network without having to upgrade or update the relays. So if you think about going from your current state to the future state, you may not always have the luxury to change a lot of the legacy equipment. Having options like this allow you to keep still an existing relay and still be part of a modern network. The other, interesting point again, thinking about upgrading substations is the protocol conversion becomes critical because you may have devices which today are just, serial in nature, and again, you want to include that into a more modern digital network, and having protocol converters could be, digital to Ethernet or serial to Ethernet as an example, or it could be converting between multiple protocols, Modbus to DNP3, for example. So those elements also allow you to gradually upgrade your existing system. I'll go through kind of two cases in terms of the segments we talked about before we kind of dive deep into energy storage and data center. So if you this is an example of renewable energy system. So this is a solar power plant, obviously multiple panels, a lot of string inverters. So the first thing is there is a lot of input information that needs to get monitored and logged. So it could be electrical information, or it could be information coming from weather sensors, as an example, that are used to optimize the performance of the system. So the remote I/O capability, having the devices, appropriate devices to collect that, and then having equipment that can log that information close to where the input is being received. So this is an example of a data an edge computer that can be used as a data logger. Then if you take the example of meters, the meters may have, as an example, a Modbus protocol, and you may want that to be converted into a DNP3 because that's what the grid operator uses. So you have applications for protocol converters. All this information that is collected by the data logger and the meters, need to be evacuated, back to different entities. So you need different levels of switching. Could be unmanaged switches closer to the edge, managed switches, and then secure routers, right? As you get closer to the core of the network, having the firewalls and so on. Also keep in mind, there are multiple entities who are looking at the information, and each of them are looking at maybe a slightly different slice of the pie. So you have the grid operator who is obviously focused on maintaining the integrity of the grid. So they are looking at real-time information, what's going on in the power plant, as well as potentially sending information back, such as set points, limit, curtail your power plant to X megawatts and so on. So the grid operator, is an entity that is looking at this communication system. Now you obviously have the asset owner, who is interested again in monitoring, the meters because they're probably kind of involved on the revenue side of things, as well as the general asset health. There may be other elements that are monitored from a O&M perspective, and then there is the aggregator. Aggregator would be an entity who's contracted with multiple of these solar plants, and they are trying to get information so that as an aggregate, they can present that to the utility and ensure that their contracts are met in terms of amount of power that they were contracted to deliver at a particular point in time. EV charging is another example. Again, multiple variations of it. On the left side, you kind of see, kind of the destination charging, if you will. So this may be distributed chargers, may still be operated by a central operator, and they may require wireless type connectivity, right? So there are devices that allow each of these charging stations to connect back to the cloud or to a central charge point operator. And on the right side, it may be let's say highway side charging station, right, hardwired here. But again, there are multiple entities involved. The charge point operator may be more involved in kind of the revenue side of things, and you may have an O&M provider who is actually looking at health of some of this equipment, who may be looking at regulating the power output and distributing the power output between different chargers, right? So depending on who the entity is, everybody's looking for a slightly different set of parameters to optimize. And again, having the solutions to allow all these different combinations is critical. The other aspect which is also important on the overall grid side is timing. Historically, it was okay to have timestamps in, let's say, the millisecond level resolution, but as systems are getting more sophisticated, that is no longer acceptable because there are applications such as synchro phasers which use waveform comparison between two different points to gather intelligence in terms of system conditions, power system faults, and so on. And even a slight difference in timestamp may point you to kind of the wrong conclusions. So here in this particular example I'm showing here, we are describing what we call the precision time protocol, or PTP. And the way it is done is that you have typically a central master clock, which is a very high accuracy clock, could be an atomic clock as an example. And then that timestamp is passed through the system. Now these devices that you see here in blue are all capable of taking these timestamps, understanding what the latency in the system is, and correcting for it, such that the time that is reported here is exactly the time that is reported at the bottom, because these devices are intelligent enough to understand how much, how many microseconds, how many milliseconds it takes for that timestamp to come from the central clock to each of the devices, and then they correct themselves and present the accurate time. So this is again an application where if you want to use some of these sophisticated algorithms, you need to be able to be using this. Also, kind of on the situational awareness side of things, we talk a lot about the hardware, but it's also critical that as you put more hardware into the system, it's important that we are able to visualize the system very clearly. So you need to have the software that is capable of identifying and clearly, to an operator showing, right, what are the communication paths and so on, which is critical for even the cybersecurity and auditing and visibility. The other piece is enhancing the efficiency, right? So when you have a lot of devices, you need to be able to configure these devices on a large scale basis, right? You don't have the luxury of doing one by one. So ability to take the settings and propagate across the system. Optimizing the operation, right? So making sure that the set points or the settings in each of the devices are backed up, such that if a device needs to be replaced, that information is readily available. The latest firmware versions are deployed, right? An ability to see what firmware versions are, then compare the latest and appropriately adjust. And then overall minimizing the downtime, right? So if there is a fault, an ability to quickly respond to it. So visualizing IEDs, detecting tampering, so making sure that there is no unauthorized, traffic that is going through. And then, another example is kind of monitoring some of the hardware, such as fiber optics, and making sure that if something is going to go bad, you have advance notice of that happening. So monitoring and alarming and so on. And all this kind of falls into the kind of the overall cybersecurity architecture. There are a lot of different protocols, a lot of different standards that are in place around the world, and it's critical that the equipment manufacturer is able to provide different options so that the end user, who is ultimately responsible for the certification, has all the capabilities, right? That in order to maintain these NERC 6 certification. So we kind of talked about a few of these different applications. So we'll kind of open another poll question where just curious on the particular application that like you are most interested in, or you work most with. It kind of gives a sense of is some of these is more useful than others. Okay, so I see like substation automation, a few of you. Data center, okay, energy storage. Interesting. I think a lot of, the majority, I think substation automation, as you would expect, because that's kind of the nerve center, followed by energy storage. So again, thanks for that input. And now my colleague Hans will take over and kind of dive deep into a couple of different applications.
All right, everybody. Just before Hans starts his section here, I'm looking at the time. Looks like we have about 20 minutes left. We might go over just by a little bit, but we hope you can stay for the whole thing. This next session, Hans is going to do a deep dive into talking about BESS and data center applications. So definitely stick around. If you guys have questions, put them in that Q&A, and we'll try to get to it at the end. If you are not able to stay for the whole thing, we can reach out to you separately after the webinar as well to answer your questions. All right.
All right. Thanks, James. And thanks, Kuru. Very insightful. So hi, everyone. I'm Hans Jen, and it's very nice to be here. We have just explored the trends and the applications in the energy sector. And I saw lots of you are interested in SaaS, battery energy storage systems, and data center infrastructure. That's good, because in this section, we will deep dive into the BESS and data center infrastructures. So let's begin with the battery energy storage systems, or BESS. And I will spend a few minutes to go through the technical details. A grid-scale BESS are complex and usually involve multiple companies to complete. So based on our experience, there are several subsystems in a large-scale project to support communication and automation technologies, including the BESS at the left-hand side, power conversion system in the middle, and the balance of plants on the right, as shown in the slide. So the BESS system has the battery cells and racks, automation, and auxiliary systems related to battery operation, so which includes battery management system, cooling, and fire suppression system. So the BESS, the BMS maintains and monitors the health of battery cells. It relies on measurement of battery voltages and temperature using variety of the sensors. It estimates the state of charge. It also detects abnormal status and coordinates auxiliary systems and sending alerts when there's an issue. For example, if one of the battery cells has an abnormal voltage, let's say maybe over voltage or over current, the controller would disconnect that battery pack until it gets replaced, so we can protect the whole system. Next to the BESS containers, there is a power conversion system in the middle, or PCS, if you will. It controls and determines when the battery should charge or discharge and at which rate. So with that, the PCS controls the electricity flow that convert between direct current used by the batteries and alternate current, or AC, of the grid. So to verify if the BESS is performing as expected, we use power quality meters to measure the voltage, current, and frequency. So that's why you see those equipment in the PCS container. When it comes to the balance of plant, the field control devices include IEDs, or protection relays, auxiliary monitoring systems, and metering. So which are the typical devices you will see in substations? So moving up to the middle part, there are two key devices on the site level, which are power plant controller and remote terminal unit, or RTU. So the PPC is the main control unit for the entire site. Its job is to coordinate all the inverters. To do it accurately, it relies on the readings from the PCC meters. So communication between PPC, inverters, and meters is critical. And RTU, on the other hand, coordinates and automates operations of the protection devices, and it also acts as a communication gateway to the utility at the right top. Site BMS is monitoring all the battery containers, and is very important both for the site owner and BESS manufacturers to manage the assets efficiently. SCADA, on the other hand, monitors the electricity flows and switchgears status. So at the top, you can see a few different key components or stakeholders. There are multiple systems that interacts with the BESS site, including BESS OEM, IPP, system operator, and utility. So I'll give you a simple example. So let's say the BESS is charged, and the bidder system gets the available energy and capacity on site and plays the bid to the energy market to sell 100 megawatts in the next 5 minutes. And if the bid was successful, the EMS sends the command through the utilities substation all the way to the substations or to the RTU within the balance of plant. The RTU will then send a command to the PPC, and as a result, the BESS site would generate 100 megawatts of the power to the grid. So this is the whole process, how the BESS involved in the bidding process and supply the power to the power grid. And the next question you might have is, how are we gonna connect this equipment in the BESS site? So there are 4 distinct networks I haven't shown in the slides to enable the communication between the key components, including the first one is the BESS container network, PCS network, substation network, and WAN or DMZ. So we will take a closer look in the next slide. So here is an example of a grid-scale BESS network architecture. In each battery container I highlight in gray, we use an EDS 2005 switch to connect those devices, including an ARM-based UC computer and an I/O logic, which is a remote I/O. So this equipment handles HVAC, fire suppression system, door access, and so on. Moving to the BMS cabinet, which is in the purple box, includes the system BMS, which is a battery management system, and the UPS. We use a Rackmount switch to connect the battery containers to the BMS cabinet. So that's why we need a high port count here. The PCS cabinet I highlight in a blue box contains the PCS controller, which work with the PPC, power plant controllers, in the control room to manage power flow. All PCSs are connected using Moxa turbo chain. Together, the battery containers, BMS, and PCS cabinets form what we call a lineup. So if you will, the number of containers per lineup depends on the specifications of the batteries, and the number of the lineup depends on the size of the project. Moving up to the control room I highlight in green, we have two sets of EMS and PPC systems, one main and one backup. So those equipment will be connected to the core network using Moxa Turbo Ring. So this system design is scalable. For example, a 10 megawatt project might use one turbo chain. On the other hand, an 8 megawatt project could use up to 25 or even 30 turbo chains. And most of the time, BESS projects require fast recovery time to avoid interruption. With this network design, network will be recovered within 50 milliseconds after a single node failure. So this is the highlights and a conceptual design for a grid-scale BESS network. Next, I will switch gears to the power infrastructure of data centers, which we can mainly split into three sections as shown at the top, including the utility power, the critical power, and then the critical load. So which provides services of power transmission, power distribution, and power quality. At the left-hand side, we can see the power is provided by the utility grid or the generator. So when the power comes in, we will first face something important, what we call a ATS, automatic transfer switch. The role of this equipment is to choose which one is the best power source. Let's say if we have power outage or the power quality issue from the main power source, which is utility, it will automatically switch to the backup power generator. Then we have a UPS and PDU to ensure the power quality is good. And the control room to monitor and control the site, as you can see at the right top. And we offer solutions to build each key component within data center infrastructure. In the commercial substations, we provide IEC 61850 switches support PRP and HSR, which is redundancy protocol supports zero recovery time. Our protocol converter mGate supports protocol conversion between BMP3, Modbus, and IEC 61850. And also in the backup generator, PCS, ATS, and also UPS, you can see our import and also IO logic and even panel computers installed in each component. And moving to the control room, we have the Rackmount or DIN rail switches to build the backbone network, which I will show you the details in the next slide. And let's begin from the bottom. So this is a network architecture of the data center infrastructure. In the power infrastructure we introduced in the previous slides, such as the generation room, electrical room, and UPS room. EDS 528E is a DIN rail switch. Those switches are used to connect those equipment to the control room at the top using turbo chain technology. In the middle section, we have chillers, water tanks, and fan wall to help keep temperature low. We use two EDS 528Es to connect this equipment to the control room as well. In the control room, there are two PTG 7828, which is a Rackmount switch, as you can see at the right top. which is a IEC 61850 certified and support turbo ring technology. So with this layered network architecture, the failover time is less than 50 milliseconds. And if you want to add network segmentation, which can be easily applied to build a secure network. So as we can see here, there could be thousands of devices in substation, BESS, and data center infrastructure. Having the visibility of the networks and situational awareness are critical, not only from operational perspective, but also from a cybersecurity standpoint. So it's important to monitor real-time network status and receive the alerts when something happens. So next, I'm going to show you a short demo of our network management software, MXV1, which is a powerful tool to provide network visibility. So as you can see, this is the interface of the MXV1. After you discover all the equipment, it will display and draw the topology like this. Once you click each icon, you can see all the detailed information at the right-hand side, including IP address, MAC address, and redundancy protocols. And here for substation, IEC 61850 substation, you can import the SCD file so that we will be able to monitor and control the IEDs in the substations. And as you can see here, MXV1 is able to monitor the goose message, because goose message is the most important Ethernet friends in the substation for protection and control. And here I'm gonna show you a cyber attack scenario, which I will inject a exactly same goose message from the top, which is the attacker. So although the goose message is the same packets or same frame, but within our switches and MXV1, we can let the user know that although this goose message is the same frame, but it's coming from unauthorized path. So we will send you alert real time so that the users can just react in a timely manner and then just doing troubleshooting and isolate the issue very quickly. So this is a quick overview and demo of the MXV1. And next, I will hand it back to Kuru.
Thank you, Hans. Very insightful. As you can kind of see, there is a lot more detail to, each of those, right? And we can get into, much more of that. So I want to kind of close out this discussion, just to kind of highlight some of the, if you kind of look at a partner, right, what are some of the things that you may want to look at? So the first thing is, I would say, subject matter expertise, right? So in Moxa, we obviously have a lot of hardware and software solutions, but the key investments that we are making are on, building our application expertise, right? We have a lot of industry experience with all the different topics we just talked about. We have, gigawatt scale installations globally, employing, a lot of these solutions. And we work a lot with the customers to work with them to create the architectures. So we are, part of the projects, from the beginning itself, and we have the technical, expertise, within the company to do that. So I would say that's one of the, the key aspects, you would need to look at, when you are thinking of, who to partner with. In addition, we participate in a lot of, a lot of the standards bodies, whether it's ISA, IEEE, VPAC. So a lot of cutting edge, requirements are, we are, we have a seat on the table, as we, deliberate and work through some of those. The product portfolio, as I kind of mentioned early on in the slides, it is important that you have a portfolio that, takes you from all the way from, kind of that analog IO input up to and including the computing side of things, right? And everything in between. And again, this is one area that, Moxa has invested and continues to invest in, including a portfolio that is very power specific, such as some of those redundancy protocols we talked about. So we both have very custom power equipment as well as a more generalized equipment, which can still be used in many of these power applications. The robustness of the product, obviously the temperatures and ambient conditions goes without saying. These installations are typically in very rugged environments. So making sure that the products have the appropriate certification, as well as some of the longevity, right? If you measure in terms of mean time between failures and those metrics, we are I would say industry leading in that. And then ease of use. So this kind of goes to everything from having appropriate network management software, ability to quickly, set, quickly commission, and if there is obviously any issue, quickly troubleshoot. So do you have the ecosystem, both from the hardware, software, network management to allow you to do that? And then as important, cybersecurity, right? So we look at, cybersecurity, kind of in a defense in depth type approach where there are things that we do at the device level, such as the various different certifications. Then we have products at the network level, such as, intrusion, detection systems. And then at the, I would say the top management level, right? Having the network management software infrastructure that allows you. So all these three need to work hand in hand, for you to kind of build, that multi-layered cyber secure installation. So in summary, I would say, we, from an electrification perspective, it's critical that the grid needs to be smarter. That's the only way you are going to be able to squeeze all those extra electrons that the demand growth is predicting. And real-time data is key to optimization. So making sure that there is enough measurement sensing that is happening, and on a real-time, low latency basis, taking all that information and then using that to optimize the grid. Security is obviously critical, and then I would say as critical is making sure that the partner you work with has the right level of expertise and experience and the product suite to help get you to where you need to be. I also want to kind of, take a minute to talk about solution days. So these are what we can do in terms of, Moxa personnel, meeting with your teams, right? Either, face to face or virtually. And we already have a set of, topics, right, that we have, done a lot of work on. Be it on the cybersecurity side or on the networking, network segmentation, and so on. And these are industry-leading experts, within Moxa, who are, willing and available to, meet with your teams and kind of, take that next step in terms of, the different, applications that we can help you with. These are not technical training, so these are, more interactive. These provide you with a lot of concepts based on best practices, right, that we are kind of seeing globally. So, this kind of, gives you an opportunity to, and James, you can kind of take to the next one.
Yeah. So like Kuru mentioned, our customers have found these solution days to be quite valuable. So we wanted to offer this opportunity to everybody here as well. The poll question here, this won't be shared. The results won't be shared with everybody, but do let us know if you are interested in us reaching out to you in setting up one of these solution days, or if you're interested in discussing probably a project that's ongoing, or if you just want to have more information about Moxa solutions, we'd be happy to connect with you on that. Okay. So moving on to our next section, which will be the Q&A. This will be the last section here for the webinar. And I'll go ahead and tee up this first one that I see here. Can you share a recommended guideline or best practice for designing a secure network for BESS?
Sure, I will take this one. So The first strategy we can use is network segmentation using VLANs or ACLs. So we can create different zones and conduits in the network. I will group the devices which have the same cybersecurity level in the same group. For example, so we can put controllers like EMS, BMS in the first VLAN and the workstations in the second VLAN. So we can achieve a better network segmentation.
Okay. Thank you, Hans. Here's another one. What type of processors do you use in your computers? And do the computers support time synchronization?
Yeah, I can take the lead. So the computers we're kind of talking about our DA series computers, which are more appropriate for these applications. They are available in multiple processor options. So for example, our latest DA 820E product line has i3, i5, i7, right? So this will be the core i3, i5, i7. The late kind of the 13th generation product line that is available. And also in addition to the processors, we have made some enhancements, including hot swappable power supplies and so on. Yeah, so in terms of the time synchronization, yes. So these products are actually designed to be capable of that PTP I mentioned in one of the previous slides as an inbuilt feature, which essentially means the computer can be part of the network and still do those latency corrections and present the accurate timestamp at all points.
Thanks. So speaking of time synchronization, here was another one regarding the switches, asking how did the switches synchronize time?
Yeah, so the switches, if you remember that diagram, we were kind of going through, on the PTP slide, the switches that are there, which are the PT series or the switches, which are by the way the same switches that allow you to do the redundancy solutions, the PRP and HSR. They also have the PTP solution, and the way these switches do it is at the hardware level. As opposed to the software level. And then there's a critical difference there, because if you are correcting timestamps in software, you are still adding some latency. You cannot completely eliminate it. We are doing it at the processor level, which essentially gives you the true pure PTP functionality.
Thanks, Guru. Teeing up the next one here. In BESS deployments, we often have an EMS managing the batteries in BESS and SCADA systems at the substation level. How does MX View 1 integrate or coexist with these platforms?
Okay, I'll take this one. So in short, MXV1 does not conflict with SCADA or EMS in the current like network in BESS or substation, because SCADA focuses on electricity flow and circuit breaker status. And on the other hand, EMS monitors the site's overall energy status. Neither of them provides visibility of the network. So to fulfill these requirements, which is strongly recommended by cybersecurity standards and regulations, MXV1 monitors network status and also provides you like real-time alerts. So MXV1 can operate alongside with EMS and SCADA.
Okay, thanks, Hans. We do have time for just one more question here for our last one to wrap it up. It is also regarding MX View 1. So cybersecurity audits have highlighted the need for better firmware management. Can MX View 1 assist with managing and upgrading firmware across our network?
Oh, this is a good one. So I've seen this request during like quite often during cybersecurity audit. And yes, MX1 supports both assets and firmware management. So users can check whether device's firmware is up to date. If not, they can do firmware upgrades directly through MXU1 to have the latest patch to patch the vulnerabilities, for example.
Thanks, Hans. All right, guys, we're a little bit over the time here, but that will wrap it up for our webinar today. We really appreciate everybody joining and sticking around. We will have a survey that will appear at the end of this session. So we appreciate it if you could give us your feedback there. I just wanted to give a last thank you to Kuru and Hans for sharing your knowledge about energy applications and also that deep dive into how to make them resilient. Thank you everyone for attending, and we hope that you found this information valuable. We'll see you at the next one. Bye.
Thank you.
Thank you.